In the last video, we drew these imaginary lines of values that the x and y could not be for the domain and range. Well, this video, we're actually going to talk about what those lines are called and how to calculate those lines. So those lines are actually called asymptotes. And this is kind of one of my favorite subjects because it feels like you're saying a word that you shouldn't say, but it's actually okay. It's okay. Oh darn, asymptotes. It's kind of fun to say. I don't know. Maybe that's just me. So an asymptote is a line, an imaginary line that continually approaches a given curve but never reaches it. So when I'm thinking of asymptotes, I like to think of that game that you might have played when you were younger with your sister or brother where you're like, I'm not touching you, I'm not touching you, and you get closer and closer and closer until they slap you in the face. Hopefully not. But that's the idea of asymptotes. You're getting closer and closer to a value, but you're not actually ever reaching that value. So it's an impossible thing to achieve. Now, when we're talking about asymptotes, there's three different types of asymptotes. There's a horizontal, a vertical, and an oblique asymptote. And what I want to do is start with what we call the vertical asymptotes. And the vertical asymptotes are the values that make your denominator equal to 0. Okay, denominator equal to 0. And these are going to have the equation x equals some number. Okay, x equals 5, x equals 2. What is the number that x equals? And vertical asymptotes will just be that line that your graph is approaching but never ever touching. Horizontal asymptotes are the other ones, horizontal. And these ones have a couple rules that we're going to talk about. Your graph could or could not have a horizontal asymptote, but if it does, it's going to be y equals some number. And this has to do with your behavior on the far out ends of your graph. So when we were doing the range, we were looking at the values of y that were not possible. And we were looking out at the very ends to see what that graph was approaching but never ever touching. That's the idea of horizontal asymptotes. And then the last one is an oblique asymptote. An oblique may also be called slant. So just be aware that it could be called slant as well. And it's just a linear asymptote. And just got a linear equation. And basically this occurs when you have the exponent on the top in the numerator is greater than the exponent on the bottom. And that'll make more sense as we go through them. But just know that they're going to have a linear equation, y equals something x plus something. I'll just do the mx plus b since that's our standard, excuse me, not standard form, but our slope-intercept form of linear equations. So it'll have some form like that. Okay, let's get into more details. So let's go into that horizontal asymptote again. Now, note, when you have a vertical asymptote, you can never ever touch it, right? It keeps approaching it, but it'll never ever 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 touch. Now, on horizontal asymptotes, the graph can actually go through the horizontal asymptote. And I know it feels strange, but it is possible for a graph to go through a horizontal asymptote because all you really care about with horizontal asymptotes is that end behavior. So at the ends, they're going to be approaching that horizontal asymptote and never ever touching it. There's a difference there. And so how do we actually figure out horizontal asymptotes? Because that's what I kind of skipped over before. Well, the idea is you're going to look at the leading exponent on top in the numerator, and you're going to compare it to the leading exponent on the bottom. When I say leading exponent, I'm just referring to the largest exponent on the top and bottom. Now, if the exponent on the top up here is less than the exponent on the bottom, okay, so maybe this is x to the first power and this is x squared. Then the x-axis is the horizontal asymptote. So your horizontal asymptote is just going to be y equals 0. And we did an example of that in the domain and range video where we talked about 1 over x, the x-axis is your horizontal asymptote. So it's approaching 0, in other words. Now, if your exponents, your largest exponents are equal, so maybe a squared up there and a squared down below, that means you're going to have to calculate the value of that horizontal asymptote. And what you're going to do is you're going to take your leading coefficients. Now, these are your coefficients in front of your x squared, or your largest exponent, and you're going to just divide them. So a over b will be your horizontal asymptote. So I think one of the examples we did in the domain and range was 5 over 1. Okay, the leading coefficients were 5 over 1. So that's where we got the 5 divided by 1. So y equals 5. That's where we got the horizontal asymptote. If you don't remember, that's fine. We're going to go through some examples. And then the last case is if n is greater than m, there's actually no horizontal asymptote. It's actually going to mean that there is a slant asymptote, or oblique, you may call it as well. So just as long as that top exponent is greater than the bottom exponent. And then to find the slant asymptote, you're just going to divide, take that top polynomial and divide it by the bottom. And this will give you a polynomial that you can go ahead and use. Now you'll just knock off the remainder if there's any remainder on there. Okay, so let's go ahead and walk through the idea of how to find the asymptotes for the following function. Now, one thing that I do suggest is go ahead and just graph this using GeoGebra so you get a visualization of what the graph should look like. So we're going to go ahead and just pull up GeoGebra because it's our favorite. Nope, just me? Okay, great. So f of x equals, now remember you want to put parentheses around the numerator and the denominator. So be careful that you're putting those parentheses around the top and the bottom or else it's going to come up wrong. So you'll see here that this is an interesting graph. It actually looks like there's about 1, 2, 3 parts to this graph. You can see one of them looks like our normal, well, 2 of them look like our normal curves, but then in the middle you've got this cubic type of looking dude. So we're going to actually explore the different type of asymptotes available. So the first thing I like to do is start with my vertical asymptotes. So I'm just going to go ahead and write vertical here. In most graphs, there will be a vertical asymptote, but it's not required, okay? So be careful, it may not occur. So over here, vertical asymptotes are found by just taking your denominator. So in our case here, this would be x squared plus 2x minus 8. Set that equal to 0 and solve. Now this is a quadratic, you can tell because the largest exponent is a 2. So we need to solve this using one of our methods for solving quadratics. And those methods we've learned are factoring, solving by factoring, and the quadratic formula. You can use either method. The easier method here would be to factor, since this is factorable. So just as a reminder, to factor this, we're just going to break it into 2 binomials. We're looking for what multiplies to give us negative 8, but then adds to give us positive 2. So it looks like what will multiply to give us negative 8 will be positive 4 and negative 2. So that multiplies to give me negative 8. And then when I add that together, I do get a positive 2. Yay! Wahoo! Then we want to take each factor and just set it equal to 0. Okay, solve that. X equals negative 4, or add 2. So we're just working with linear equations now. You can see that I now have 2 vertical asymptotes, x equals negative 4 and x equals 2. Let's check to make sure I did that correctly. I'm going to bring up my GeoGebra. And I'm just going to go ahead and type in those vertical asymptotes. X equals -4. Okay, if you didn't notice, it did bring in that black line, which it does look like that graph is approaching that vertical asymptote, but never actually touching the vertical asymptote. So that's a good sign. Now I want to go ahead and make this dashed just because it's an imaginary line. So I'm just right-clicking on that line and I'm clicking on Properties. And I'm going to change the style, the line style, to just this dashed option. This is not required. I just like to do that. Okay, and then just exit and you'll notice, ba-bam, I've got a dashed line, which means it's an imaginary line. And you can see that my graph is approaching that line but never touching that vertical line. Let's do that again with my other asymptote, which should be on x equals 2. Well, it looks like that is good as well. Right-click Object Properties, change that style to dashed, and we've got a beautiful asymptote right there at 2, x equals 2. So we do know we came up with those correctly, and there's no other vertical areas that are separated, which means we did it correctly. Okay, so you know what, let's go ahead and change those colors too. I'm going to change the color to green. And the only reason I'm doing, oh God, that's terrible. It's a terrible green color. Okay, let's do it. I want you to be able to see it. I just want to make sure you can notice that versus the black. So hopefully that's obvious. Now we want to go ahead and decide, is there a horizontal asymptote or a slant asymptote? To do that, we need to look at our leading exponents. Our leading asymptotes, that does not want to delete. So our leading asymptotes, look at the variable. It looks like the leading asymptote on top is 1 and the leading asymptote on bottom is 2. Since the top, 1 is smaller than 2, right, our exponents. Since the top is smaller than the bottom, there is a horizontal asymptote. And if you're not sure where I'm getting this, it's from this one. So if n is less than m, okay, n is less than m, there is a horizontal asymptote, and that asymptote is your x-axis or the line y equals 0. I'm just going to write y equals 0 here, simply because the top was smaller than the bottom. And since the top was smaller than the bottom, there's no slant asymptote. Boom. So let's go ahead and graph that horizontal asymptote on the graph just to make sure that in fact as we reach out, look to the very ends, positive infinity, negative infinity, let's graph that y equals 0 line. Now this is going to be hard to see, so I'm going to use red and I'm going to dash that so we can see that. Okay, so notice on that x-axis, which is the y equals 0, as we get farther and farther to infinity, it does approach that line, and it's going to do the same thing on the opposite side as well. You can go ahead and play around with that and notice it does approach. Now this horizontal asymptote, notice the graph does cross it over here, but that is okay for horizontal asymptotes. It's just not okay for vertical. So just be cautious of that. Okay, so those were our 3 asymptotes. Notice that I always write asymptotes as equations. Please make sure that you're doing so, because they're invisible lines. Okay, so let's look at this example. So it's x plus 4 all over x squared plus 1. Now the first thing we want to do is go ahead and graph that function. So we're just going to grab GeoGebra, clean it up if you need to, delete your old functions, all that happy jazz. Then we're going to use that input line, just f of x, equals, remember x plus 4 should be in parentheses, divided by x squared plus 1 in parentheses as well. Now, this one's a little bit more interesting because if we look at it, there's no real breaks in the graph. It's just actually a continuous line, which is interesting because it's a little different than what we've seen. Let's talk about why that is, though. So let's look at our first item, which is vertical asymptotes. Well, there's no breakup in the graph, so I'm having a feeling that there's not going to be any vertical asymptotes. But let's double check by doing our calculations. So we're going to take that denominator, x squared plus 1 equals 0. Now this is a quadratic, and I'm actually just going to solve it by subtracting 1 from each side. X squared equals -1. If I were to solve this, I can just square root both sides. Since there's not 3 terms up there, I don't have to worry about using factoring or anything like that. So this is x equals the square root of -1. What's the square root of -1? You may ask. Well, it's that imaginary number. Well, we're not working in imaginary numbers for the graphs. So what that means, be positive or negative since we're taking the square root of an imaginary number, that means there's no vertical asymptote. If you get an imaginary number, there's no vertical asymptotes. And we can see if we look back on that graph, there's no breaks, no vertical breaks anywhere along that graph. It's all continuous, meaning that there's no vertical asymptotes. That's the connection between those two ideas. Now there is a horizontal asymptote, so let's explore that one. So remember, to determine if there's a horizontal or a slant asymptote, we need to look at our exponents. Now it looks like the exponent on top, the largest one is 1, and the largest exponent on bottom is 2. So that means the bottom is larger again. And remember, when the bottom is larger, that means your horizontal asymptote is y equals 0. It's that x-axis. So if we look here, we look at our graph, we can go ahead and y equals 0. Boom. Notice that the graph does go under, but then it starts to go back up and it starts to approach that y equals 0 from underneath. That's what's happening here on this graph on the left-hand side. On the right-hand side, notice that the graph is approaching from the top. And I reference these things because as you get into calculus, you'll be doing more with where is it approaching, and that's actually called limits, and that's going to be a huge part of calculus. So this week's actually pretty important for your success when you get to limits, in other words. So keep that in mind. Okay, so as we look at this graph, there's only that one asymptote. I'm going to make it a little bit more obvious because it looks like it's hiding. I'm going to use orange. See if we can see that better. Oh, we can see that better. So if you look, there's that orange dashed line, so it is approaching y equals 0. So there's only one asymptote for this function. Now we have 2 more examples. So the next one is -3x squared plus 2 all over x minus 1. So let's start by graphing that as well. Now I'm going to have to clean up this graph real quick. I'm going to go ahead and put in f of x equals, of course, the top has to go in parentheses, plus 2, close parentheses, divide that by, again in parentheses, x minus 1. Okay, so I'm going to have to zoom out here a little bit. There are still 2 parts of the graph, but they're kind of funky. They're kind of like V's going either direction. Interesting, interesting. And so it doesn't look like there's a horizontal because they're not approaching it as you go to infinity, but there does look like there's a vertical since there's a break and it's not continuous. And it almost looks like there's a slant asymptote going downwards. But you know what? Let's check by doing the calculations. So first thing we want to check is our vertical asymptote. I'm not spelling it out anymore. You can if you would like to. So just take your denominator, x minus 1, set it equal to 0. This is awesome because this is just a linear. So we're just going to solve by adding 1 to both sides. X equals positive 1. There is my vertical asymptote. Of course, I want to graph it on my function just to make sure it looks good. And it does. It does look, of course, you'll have to zoom in because it almost looks like it is touching, but it's not actually. You just haven't zoomed in close enough. So let's use green and dash that line again. Boom. Look at that beautiful asymptote we've graphed. It looks great. Wahoo. Now, remember we said, oh, it doesn't really look like there's a horizontal asymptote, but it looks like there's a slant asymptote there. Let's go ahead and look at that a little closer. So again, we need to compare our exponents, the largest exponents on the top and the bottom. Now, the largest exponent on the top is 2, and the largest one on the bottom is 1. That means the exponent on top is actually greater than the one on bottom, meaning that there is no horizontal asymptote, but there is a slant asymptote. Okay. So remember, to find the slant asymptote, you actually have to divide these two. Now, since you're dividing by a binomial, we can actually use synthetic division that we did last week. So I'm going to go ahead and just use synthetic division. I'm dividing by x minus 1. Got to flip what I'm subtracting by, the sign of it. So this becomes positive 1. Now underneath, I need to go ahead and put the coefficients. So it's going to be negative 3. Now it's missing a term. It's missing that x term. Whenever it's missing a term, I need to put in 0 just in case. And then 2 will be the last one. Now let's go ahead and solve this. So just drop down the first one, multiply, add again, multiply again. That gives you a remainder of 1. So it does not divide evenly because you're not getting a remainder of 0, but it does leave you with the equation negative 3x minus 3. Remember, when you're changing this back into equation, you take the largest exponent and you just subtract 1. So y equals negative 3x minus 3. And I really squeezed that on there. Remember, we drop off the remainder. We don't care about that remainder. So let's graph it to make sure it is. So y equals negative 3x minus 3. Ooh, look at that. It fits the graph perfectly. Enter. And we're going to go ahead and change that to a different color and dash it because it is that invisible asymptote. It's not actually part of the graph. It's just representing what it's approaching to help visualize. So got some Christmas colors going on there, but you can kind of see the graph as we get to farther away. It is approaching that line. It almost is like the fencing that keeps the graph in place. So that's another way to think of your asymptotes. So this one, we did have 2 asymptotes. I have one more example that I want to show you. You know what? I noticed that I didn't do any that have the same exponent, so I'm going to go ahead and just change this. Let's pretend that's a 2. So I'm going to use black and just pretend that that's a 2. So for fun, let's change that to a 2. Great! And then let's go ahead and graph that function. So delete our old ones. Boom, 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 boom. We're going to graph f of x equals, on the top is x squared because we changed that to x squared, divided by 2x squared plus 5x minus 3. Okay. Well, that just looks lovely. There looks like there's 3 parts, and it almost looks like there's 2 vertical, then maybe like a horizontal. Let's see what we come up with, though. Okay, so let's start with our vertical. Yeah, I always like to start with vertical asymptotes. So again, you set your denominator equal to 0. 2x squared plus 5x minus 3. set that equal to 0. Now this one I'm going to go ahead and factor. I'm going to use the slide and divide method since it's a trinomial with a leading coefficient. Feel free to use whatever factoring method you feel more comfortable with. So slide just means that I'm going to take that first coefficient and multiply it by the last to get me -6. Then I factor it. So this is x plus 6 and x minus 1 multiplies to give me -6, adds to get me +5. Go ahead and divide by that leading coefficient. So we just take each of our numbers, divide by that leading coefficient, and actually for our problem we can just reduce. We don't actually have to bring that denominator back over front, and you'll see why in a second. So this is x plus 3 and then x minus 1/2. I just simplified that. Now set each of these equal to 0 and solve. So x plus 3 equals 0 and x minus 1/2 equals 0. Solve by subtracting 3 from each side. So x equals -3 is a vertical asymptote, and adding 1/2, x equals 1/2 would be another one. So you have two vertical asymptotes that of course we can go ahead and graph real quick. X equals -3 and x equals 1/2. Boom, they do look like they fit in that graph, so it looks like we did those correctly. It's just a great way to check yourself that you did that correctly, honestly. I just like it to be perfect. It doesn't look good. It bothers me, so there. Oh, boom, look at that. It looks like our fencing that puts our pieces in line, right? That our pieces are almost touching. Now there is one more. We need to double check if there's a horizontal or a slant. It looks like there's horizontal, but how do we know? We have to check our exponents. So this time our largest exponents on the top are 2 and on the bottom are 2. So that means that the exponents are equal. When the exponents are equal, we have a horizontal asymptote. Boop. And basically, so 2 equals 2, our exponents are equal. When you have two exponents that are equal, you need to go ahead and take your leading coefficient on the top and divide it by the leading coefficient on the bottom. Now the leading coefficient on top is just going to be 1. The leading coefficient on bottom is just going to be 2. So this looks like we have a horizontal asymptote at y equals 1/2. Let's double check to make sure that looks correct though. So we're going to go back to our graph and just graph y equals 1/2. Not 1.2, but 1/2. Boom. Now, I'm going to go ahead and change the color of that so we can see it a little bit better. Hopefully that works. Okay, so you'll see here on the left, it does look like it's approaching that line from the top. Okay, from the top it's approaching ever so slightly, and it doesn't actually cross that line, so that's good. Now, on the other side, it does look like it goes down below the line, but it actually comes back up and is approaching the line from the bottom. That's okay for a horizontal asymptote because remember, we're looking for that end behavior on either side. So here, it is approaching that blue line as we're getting closer. So we did correctly calculate the 2 vertical asymptotes and the 1 horizontal asymptote. So this example had 3 asymptotes. So just remember that asymptotes, you can have vertical asymptotes, you cannot. You could also have horizontal or slant asymptotes. One or the other will usually happen. And remember how they're connected to domain and range. They're telling you which values are not possible for those x and y values. So it's a handy little guide to have. So work on those, and if you need to, there's plenty of other examples online that you can go ahead and check out as well. So good luck.